Well, here we are in question number 2. We've already done A. We've got our 1 point for this. In the previous video, you can see how that was done. The global average of this question was 4.8 out of 10 possible points. So let's get a few more points. We've got 1 already. As you can see, there's plenty of room here to answer these questions. The format for the FRQ booklet has plenty of space, and you're going to need a little bit of that space because you've got a lot of calculations to do here. So let's focus now on B, C, and D. It's got a lot of points in there. Typically, there's about 3 to 4 points per page. So let's attack B. A student conducts an experiment to determine the composition of a mixture. Be very careful. When you see a mixture, that means that we're probably going to have to find out something that is within that mixture. So this is not pure NaHCO3. It's a mixture of NaHCO3, they give us a molar mass, and Na2CO3. Now remember, at the beginning of the problem, we were talking about a reaction where NaHCO3, baking soda, sodium hydrogen carbonate, decomposes into our washing soda, sodium carbonate, carbon dioxide, and water. So we've got a mixture of the baking soda and carbonate. And remember, sometimes when you're working down here, you're going to have to go back up to understand what's happening. And here it is on this page, the equation that's going to be critical for answering this problem. The student places the sample of the mixture into a pre-weighed test tube that is attached to a container that holds a drying agent. I got a video of the drying agent that I'll show you later. The student heats the test tube with a Bunsen burner for 10 minutes, during which time all of the water, okay, now this is something we know about water, which is here in the reaction, produced by the reaction, they warn us about that, is captured by the drying agent. The following table shows the student data recorded during the experiment. Okay, here is the table. Now, what's the question? Calculate the number of moles of NaHCO3 present. We've got to calculate this in the mixture, in the test tube, before the reaction was initiated. Well, the reaction occurred and made water, so that's our hint. Now, tables. Hint on a table. Typically, in an experiment, you've got the weight of the empty equipment, and then after, weight of the equipment after drying or something like that. You're going to have to do some subtracting. Simplify that for yourself by labeling what really is there. Take these 4 rows and change them into 2 pieces of data. The first row, test tube, and mixture. So the difference between these two is the mixture that they're talking about. These 2 rows, drying agent, and water. Okay, after the reaction. So this gives us the water. So we now have the water and the mixture, simple by a subtraction. All we have to do is get our calculator out. So let's do the subtraction. I'll take the value for the mixture and the test tube, 17.648, minus the test tube all by itself, 15.825, and get just the mass of the mixture, 1.823 grams. This is the mixture all by itself. Let me double check that. It's worth doing, especially in subtraction when you've got all these values. It's easy to mix them up. 17.648, 15.825, 1.823 grams. Note that we are doing a subtraction, so we don't worry about significant figures. Instead, we look at columns, and this subtraction is good to a milligram. That's a good balance. So we leave that milligram value in there. Now, the water, same thing, 2.303 minus 2.134, double checking the numbers. Yes, they're there. And we've got our mass of water, error, that didn't make any sense. 4 grams? No, we can't have more water than we had baking soda. So we know this was a mistake. It should have been 2.303 minus 2.134. good lesson here. Check to make sure your answer makes sense, because it's easy to make a easy mistake like that. Here we go. This makes sense. 0.169 grams of water. Again, good to 1,000th of a gram. All right, there's our water mass. 1.69 grams of water. Now let's go on to B. Calculate the number of moles of sodium hydrogen carbonate present in the mixture in the test tube before the reaction was initiated. We know this reaction occurred and made this much water, so therefore this much sodium hydrogen carbonate, solid, notice sodium hydrogen solid, the pure stuff, must have been used to make that. Therefore, if we know the moles of water, we can find the moles of sodium hydrogen carbonate. And notice this is what they want for this problem, the number of moles that are present. We know our water. Our next logical thing would be to pull our calculator up again, take that grams of water that we know, pure substance, and divide it by its atomic mass, one that I hope you memorized. Please, you should know the molecular mass of water divided by the molar mass. That gives us the number of moles of water. But this is what they set this up for, stoichiometry. They want to make sure that you know that it takes 2 moles of baking soda to make 1 mole of water. So therefore, times 2. Our answer is 0.0188 moles of sodium hydrogen carbonate. They did the subtraction here, but you can just show a little caret there. And then once you've got that 0.0169 grams of water, you would show divided by 18, multiplied by 2. This is done beautifully, but if you were just written the numbers down, that's all the proof they need. And then we have our answer, 0.188 moles of sodium hydrogen carbonate. Let's see what the values are in terms of the point values. Mass of water, you get 1 point if you had the right number of significant figures. If you kept it to the 1,000th and had 0.0169, that's fine. Now, if you added an extra sig dig here, you would have gotten it wrong. They have 1 point that's awarded for the sig figs, and this is most likely the one. It's usually a subtraction or an addition that's involved with a lab report. So there's our 1 point there just for the mass of water. Then we end up getting another point for the moles of sodium hydrogen carbonate. Check if we answered the question. Calculate the moles of sodium hydrogen carbonate present. Yes, we've written that down. This is our moles, 0.0188. So let's go on to C. Determine the percent mass of sodium hydrogen carbonate in the mixture. Now, we've got the mass of the mixture, and this says calculate the mass percent. We need to have the mass of the sodium hydrogen carbonate. That's going to be the next part of the problem. So we've got the moles of sodium hydrogen carbonate. All we've got to do is change the moles into grams and use this mixture. So let me get my calculator out again, and I've got the moles of the sodium hydrogen carbonate. I didn't clear it out because most likely I was going to use it again, so I don't have to retype that in. All I got to do is multiply by the molar mass of sodium hydrogen carbonate, which they gave us in the problem. You can go up there and look for it yourself, but this would be the mass of sodium hydrogen carbonate. Now let's look at that, 1.58 grams, and our mixture has 1.83. Well, that makes sense. We should have, this is a mixture which has extra sodium carbonate in it, so the amount of sodium hydrogen carbonate's got to be less than that. So let's now go and find the percent sodium hydrogen carbonate in this mixture. So divide by 1.823, double check that number, 1.823. Then, of course, multiply by 100 for percent, 100, or you can move the decimal point. A reasonable value, 86.4%. We did the calculation. Make sure that you show your work. Don't just, you did that in your calculator pretty much easily in your head, but you've got to prove that you did some calculations. Here, show 0.0188 times 84. By the way, if you had the wrong number of moles of sodium hydrogen carbonate, as long as you were consistent and multiplied by 84.01, you would get the point. You're not double penalized. If you did this answer incorrectly, don't worry about it for this problem. Now, whatever you had here, you should be multiplying by 84 to get 1 point for the mass of sodium hydrogen carbonate. And then, of course, our ratio, this is the sodium hydrogen carbonate over the mixture. That's what it says. Sodium hydrogen carbonate, here it is, sodium hydrogen carbonate, slash, in the mixture. And we have that mass of mixture. So our points that they have awarded this, number of grams of sodium hydrogen carbonate dependent on your moles. Now, if you didn't know how to figure out these moles, write a number down and use that here so you can get this next point. Don't give up on C because you couldn't get B. Write down some number for the moles of sodium hydrogen carbonate, use it here to prove that you can change moles into grams. And of course, we've got our percent mixture. They're going to give us 1 point for that too. Mass percent. Here we are still on question number 2. We had 1 point for the redox. We got a point for the mass of water. If you had the right number of sig figs, you got a third point for the moles of sodium hydrogen carbonate. And if you figured out the grams of sodium hydrogen carbonate, you got another. And if you had the percent by mass, then you've got 5 points. The global average on this question was 4.8, and you're at 5 already, and we haven't even got through D, E, and F yet. So doing nicely. This far, you'd probably be a level 3. So let's keep on going. And we just finished the percent sodium hydrogen carbonate. Now, if the student spills some of the mixture out of the test tube after weighing the test tube and mixture and before heating, how would this error affect the mass of sodium hydrogen carbonate calculated and justify your answer? Okay, we've got to say how it would affect the mass percent and justify it. These can be a bit tricky, but again, we've set things up nicely because of this little comment that we've figured out. We know what the mixture is, 1.823, that we get when we weigh the test tube and the mixture before heating. So this is not going to change. If a student spills the mixture after weighing the test tube and mixture, so this 1.823 grams is the same. How does this affect the mass percent? Well, think of an extreme. Imagine if somebody spilled all this mixture. So instead of having 1.823 grams, we had nothing in there. How much water would they produce on heating? Well, if they spilled all of it, they wouldn't get any water. Our mass of water would be smaller because we spilled some of the stuff that makes the water. So we would say this 1.823 grams is the same because we spilled after we weighed it. But because we used the water to find the grams of sodium hydrogen carbonate, we get less sodium hydrogen carbonate, and this becomes smaller, therefore a smaller percent. We didn't produce as much water, therefore we figure there wasn't as much sodium hydrogen carbonate in them. So just this little calculation saying because we have less water, smaller sodium hydrogen carbonate, this is all you need to end up showing. Here, 1 point earned for the correct answer and justification. In this case, you had to have the answer and some sort of proof that you came up with this result. Okay, so that's 6 points. Now we're getting close to being 60% of the 10 points on this FRQ, which gets us close to the level you'd expect for maybe a 4. Well, that's A, B, C, D. Well, the next video will take care of E and F, and maybe we can get to a level 5. I promised to mention a little bit about the absorption of the water in this reaction. When they heated the sodium hydrogen carbonate, they trapped the water in these little tubes that are packed with this desiccant. Now, the desiccant is Drierite, and it's got an interesting history. Here's their video on their product.
Selecting an effective desiccant for her lab. While choosing a desiccant may seem like a pretty dry topic, desiccants are important for the protection of hygroscopic materials and to prevent mildew, corrosion, rust, or other deterioration caused by humidity. Drierite, for example, can dry air and gases to a dew point of -100 degrees Fahrenheit or nearly 0% relative humidity at ambient temperatures, much lower than can be achieved by other desiccants. By forming a chemical bond with water, Drierite maintains a consistently dry environment over a wide range of temperatures, and with available color-changing indication, you'll know exactly when it's time to refresh or regenerate your Drierite.
The vapor with water, when it gets into this tube, it is absorbed by the calcium sulfate, makes a hydrate, and then, of course, it will end up weighing more. Drierite's been in business for a long time, and I'm sure you've seen some indirectly. If you open up a package, you'll find very often a little sachet in it that has, if it has a white powder or a blue powder, it contains Drierite. That prevents moisture from being in that package. The company was established by a chemistry professor who was investigating, he's a PhD in Ohio State, calcium sulfate and how it absorbs water. He set up a company, and they've been in business ever since. They got 21 employees right now, but if you want to absorb some water and be able to measure it quantitatively, and then heat the stuff up and regenerate it, this is your stuff. Drierite, and you'll find it at any chem lab. They've got this characteristic label. So that's our absorbent, and here you can see what it's typically packaged in. In this case, there's a desiccator where they've got the blue stuff at the bottom, and if you've got something you want to dry out, you dump it in here, close the vessel, and this Drierite will keep the humidity down to 0. And you can just take it out of there, put it in an oven, heat it to about 300 degrees, and it'll be as good as new, and you can reuse it. The absorbent, Drierite.
A, B, C, D, and we're ready to get on to the last part, E and F. So, next video.